Hi, this is Jeremy from Basic Science 2. Today, I'm going to discuss about the human eye, vision defects, polarization, thin film interference, and Young's double slit experiment. So first, the human eye. The human eye works like a camera. Light enters through the clear cornea, passes through the adjustable pupil controlled by the iris, and is focused by the lens onto the retina at the back. The retina's light-sensitive cells, rods, and cones convert this image into electrical signals, which travel via the optic nerve to the brain, which then interprets them as the images we see. The cornea is the eye's clear dome-shaped outer layer at the front, acting like a window that protects the inside of the eye and provides the majority of its focusing power, bending light to help you see clearly. Iris, the colored part of the eye, a muscular diaphragm that controls the pupil's eye size, regulating the amount of light entering the eye, much like a camera's aperture, adapting vision for bright and dim conditions. Retina is the light-sensitive tissue lining the back of your eye, acting like the film in a camera. It captures focus images, converts them into electrical signals using photoreceptor cells, rods for low light or motion, cones for color or detail, and sends these signals via the optic nerve to the brain, which interprets them as vision. The optic nerve is comprised of millions of nerve fibers that send visual messages to your brain to help you see. Crystalline lens. The crystalline lens is the transparent biconvex structure behind your iris that focuses light onto the retina, allowing clear vision at different distances. The human eye is crucial as our primary sensory organ, allowing sight, color perception, and depth, enabling us to navigate, learn, reading and watching, and interact with the world by converting light into electrical signals the brain interprets as messages, also helping regulate circadian rhythms and balance. So let's proceed to vision defects. Vision defects are common eye conditions, mainly refractive errors where the eye doesn't bend lightly correctly, causing blurred vision for near or far objects, including myopia, the nearsightedness, hyperopia, farsightedness, and astigmatism, irregular focus, and age-related presbyopia, trouble focusing up close. So first, the myopia. What it is, difficulty seeing distant objects clearly. Close objects are sharp. Cause, the eye is too long or the cornea is too curved, so light focuses in front of the retina instead of on it. Correction, concave, diverging lenses or refractive surgery, in other words, LASIK, to spread light before it enters the eye, so it focuses correctly on the retina. Second is the hyperopia or farsightedness. It is a difficulty seeing close objects clearly. Distant objects may be sharp, mild cases, or blurry, severe cases. Cause, the eye is too short or the cornea is too flat, so the light focuses behind the retina. Correction, convex, converging lenses or refractive surgery to focus light onto the retina. Presbyopia is an age-related difficulty focusing on close objects, usually starts around 40 to 45 years old. Cause, the eye's lens loses flexibility over time, making it hard to adjust shape for near vision. Correction, reading glasses, convex lenses, bifocals, progressives, with different lens power for near and far, or multifocal contact lenses. And the fourth one is astigmatism, blurry or distorted vision at all distances, near or far. Cause the cornea or lens is irregularly shaped like a football instead of basketball, so light focuses on multiple points instead of one. Correction: cylindrical lenses in glasses or toric contact lenses, which correct the uneven curvature. Refractive surgery can also treat it. So common vision defects. So farsightedness, nearsightedness, and astigmatism. Farsightedness: insufficient refractive power to focus rays on retina. And nearsightedness: excess refractive power rays. And the astigmatism: asymmetric refraction focuses light in different planes at different points. Vision defects occur when light doesn't focus correctly on the retina, causing blurry vision but are corrected with specific lens: concave for myopia, convex for hyperopia, cylindrical for astigmatism, bifocals for presbyopia, or refractive surgeries like LASIK to reshape the cornea and achieve clear sight. So now let's move on to polarization. What is polarization? Polarization of light is when the light's electric field oscillations, normally random in all directions, are restricted to vibrate in single plane, like horizontal, vertical, or diagonal. While natural light is typically unpolarized, it becomes polarized by reflecting off surfaces, causing glare. Passing through filters like polarizing sunglasses or scattering, allowing scientists and engineers to control light for applications in LCD screens or 3D. So there are three types of polarization, which is the linear, circular, and elliptical. Linear polarization describes an electromagnetic wave like light or radio waves where the electric field oscillates along a single, fixed straight line, a specific plane as the wave travels rather than rotating or varying in different directions. Circular polarization: an electromagnetic wave where the electric field vector rotates in a circle perpendicular to the wave's direction of traveling, forming a helix as it propagates, created by two perpendicular waves of equal amplitude and a 90-degree phase difference. It's classified as right-handed clockwise or left-handed counterclockwise, depending on the rotation's direction as viewed by the observer. Elliptical polarization is a type of electromagnetic wave where the electric field vector traces an ellipse as the wave propagates, a general form that includes linear, flat line, and circular circle polarization as special cases, resulting from two perpendicular waves with unequal amplitudes and phase difference. In simple terms, light polarization is like a rope wave vibrating in all directions, up, down, sideways, versus being forced to vibrate in just one specific direction, like only up and down, by passing it through a special filter such as polarizing sunglasses. Normal light waves jiggle randomly in many planes, but polarizer blocks all but one plane of vibration, making the light ordered or polarized, which helps reduce glare and enhance images. Now let's move on to thin film interference. Thin film interference is a phenomenon causing colorful patterns like on soap bubbles or oil slicks. When light reflects off the top and bottom surfaces of a thin layer, with waves interfering constructively or destructively based on the thin film's thickness and light's wavelength, leading to visible colors. This interference depends on path length difference, refractive index, and phase shifts, often 180 for reflection of denser medium, creating bright colors where specific wavelengths interfere constructively and dark areas where they So this is example of thin film interference, the water with oil slicks and the bubble. Constructive interference means two or more waves meet and combine to form a new, stronger wave with a larger amplitude, happening when their crest or trough align perfectly, adding their energy together. Destructive interference when two or more waves overlap and their amplitudes cancel each other out, resulting in a wave with a smaller or zero amplitude, often happening in when a wave's crest meets another's trough, causing a reduction in intensity or complete cancellation, like in noise-canceling headphones or anti-reflective coatings. Proceed to Young's double-slit experiment. Young's double-slit experiment, performed by Thomas Young in 1801, is a foundational physics demonstration providing light behaves as a wave, not just particles, by showing light passing through two slits creates an interference pattern of alternating bright, constructive interference and dark, destructive interference bands on a screen, a hallmark of wave phenomena where waves add or cancel out. A concept known as wave-particle duality. When particles pass through two slits, they create interference patterns, suggesting they act as waves and go through both slits simultaneously, interfering with themselves, yet they arrive as discrete particles on a dictator screen, behaving as if they pass through only one slit if observed, revealing the profound strangeness of quantum mechanics where observation changes reality. The experiment shows that when electrons or photons are fired at a screen with two slits, they behave like waves, creating an interference pattern. However, when they are observed or measured, they behave like particles and create a pattern of two distinct bands.